So welcome everyone, and thank you so much for coming today. I am Fatih Aranolo, and I am a member of the mining department seminar committee. The committee organizes the seminar series and invites speakers to come and address students, faculty, and external industry professionals on a variety of mining-related topics. Since we are Zoom today, I would like to request that everyone keep their microphones muted during the presentation and unmute them only to ask questions during the Q&A session. To help everything run as smooth as possible. Just as a reminder to everyone, we will be recording this session so that you can watch it on our YouTube channel after the seminar. Today, I would like to welcome Richard Bailey. Thank you so much for speaking with us today. Richard, very experienced professional with a demonstrated history of managing large teams of and software developers to deliver strong, robust solutions to the control and automation industry. Having introduced numerous successful products to market, Richard has strong entrepreneurial skills with a focus on delivering value to his customers. Richard is a skilled and professional manager with a strong background in process control, enterprise software, control systems design, SCADA, and professional services. Richard Bailey will be talking to us today about their work with leveraging digital platforms for inventory management for mining. Without further ado, please welcome Richard. You have the mic.
Thank you very much, Fatih. So yes. Today we're going to talk about some of the challenges we have in mining. When we talk about digital integration, one of the key things we need is good quality data feeding into those software systems. So I'm going to use the Rockwell Mining Operations Management Suite as an example, but hopefully a lot of the information we impart today will be generic in nature across the industry. And I've worked in a whole bunch of mining industries over the last 30 years, from coal to iron, gold, copper, uranium, and they all have very similar challenges when it comes to the data and the digital side of technologies. So we'll talk about some of those challenges. We'll talk about specific types of software that can solve some of those challenges and what people are trying to get out of those types of systems. So we'll try and keep it in industry agnostic across different mining types, and we'll try and impart some knowledge. And at the end for Q&A, it'd be great to get some feedback from people and questions from people. So in mining, we've got specific challenges around the data. What people are trying to get out of the data at mining is what grade is going on the ship. Are we inside spec or out of spec? What's the feed blend coming into the process plant? Is that going to impact the process? So a lot of the types of data we're dealing with are material quantities and material grades. And the problems we have with that type of data is that the timeliness of data, the different systems that supply those pieces of data that we bring together are all disparate, and bringing them together becomes a challenge. So I'm going to jump through some slides initially just to talk about the challenges. I'm going to jump into a demonstration of software that solves some of those challenges. And I'm going to, because we've got a very technical audience here, I'm going to dive into a bit of the back end of how the software thinks about data so that you guys get an idea of how things get modeled in the back end. So let's get started. So in mining, depending what industry you're in, the grades of feedstock, whether it's gold or copper, uranium, is getting depleted. So it's getting harder and harder to get good grades out of the ground across a lot of industries. And in mining, when we look at OEE is a metric which tries to summarize the performance of your process or plant as a single number. It's an indicator, there's a lot of detail behind it. But an OEE of 27% in underground is quite low. In manufacturing, you'll be up around the 80%. In oil and gas, you'll be up even higher. So in underground mining and open pit, OEE tends to be low. It's partly the nature of what we're doing. There's a lot of stop-start type operations in mining, but there's also a lot of room there for improvement. The challenges in mining are when your OEE is low, you're not utilizing your assets well, you're not getting good grades out of it, and that's costing us money. So what we want to do is try and get things like the OEE, utilization, availability, yields, recoveries, all those numbers up as high as possible. So when we look at data, we've kind of got this dichotomy in mining of too much data, but not the right data. So I've worked in companies where they drop in a big historian and they record everything they can from the process control system in their fixed plant assets, and they end up with tens of thousands or hundreds of thousands of tags being logged at high granularity. There's an enormous amount of data sitting there available to be used, but nobody's using it. They're picking a few key elements out of it and the rest of the data just sits there forever unused. So mining companies are using typically less than 1% of data, according to McKinsey. And then the other dichotomy of that is, as well as all that rich data that they've got sitting there in the historian, there's a whole bunch of other data which we need, which isn't being captured. And that comes down to manual data capture. If we look at drill and blast operations, they're notorious for not recording data electronically. Fleet management systems tend to be isolated and not integrated. So there's data that is either not being captured or it's captured somewhere else and it's not accessible to us, or there's an enormous amount of data that is not contextualized and people can't use well. So that's kind of the twin dichotomy of data in mining. How do people use that? So there are systems in most mine sites which are doing some level of reporting, whether that's Excel based or it's automated. There's always some level of reporting being done, but each department will have its own system typically, and they will report similar things using different algorithms, similar things using different tools. So you'll end up with availability being reported from the maintenance department and the process department, and there'll be different numbers. So all we end up with is inconsistent definitions, lacks of standards, and that results in a lack of trust in data. Quite often the reports that go up to management have been manually compiled, people cutting and pasting data from those different sources into PowerPoints or Excel, and then feeding that up to management. So coming back, I'll try and do some real world examples today. So there's a zinc mine up in the middle of Queensland in Australia, where their drill and blast team record their drill and blast operations, meters drilled, meters blasted on paper. At the end of shift, they come and put it in a pigeonhole, and there's a metallurgist, fairly expensive resource, who spends 4 hours every morning manually punching that into Excel and copy and pasting data between Excel files and running macros, pulling data from emails and dropping it into Excel to build up their daily reports. 4 hours every morning for a fairly expensive resource, just compiling data from those different sources. So even today, 2021, we've still got paper and Excel being a key part of the reporting process on a lot of mine sites. What that comes down to is a heavy reliance on key individuals, especially if people have built macros in Excel or a bespoke access reporting system hooking onto the data. As soon as that key individual moves on, the system's unmaintainable. So that's what we want to try and avoid. We want repeatability and systems in place which will continue to function correctly, even if individuals move around to different places. The other thing that I see in mining, every site I go to, they have a morning meeting and they focus on what happened yesterday. What I see repeatedly is that's the only focus. It's what happened yesterday, and a little bit of finger pointing and blame game going on. What we really need is a system where people can say, what happened yesterday? Okay, let's resolve that. How do we avoid that today? But then take a step back and say, what's been happening over the last 3 months, the last 6 months, the last 12 months? What are our systemic causes of failure? What should we focus continuous improvement initiatives around to remove those systemic causes of failure from operations? There's a lot of sites will have a capital improvements team, and what I repeatedly see coming from them is initiatives going in where they measure the success of an improvement initiative by whether they finished implementing the initiative. They don't actually go back and benchmark before and after to validate that the outcomes they needed actually got addressed and achieved. So no benchmarking, little return on investment validation within businesses for improvement initiatives. They stand them up and they spend a fair bit of time justifying them initially, then they go and implement, and as long as the implementation is successful, tick the box, they're done. So having systems in place that just have that 12, 24, 36 month history sitting there to allow you to automatically correlate changes in performance across different points in time when initiatives get deployed, will allow you to do that sort of validation much better. The other thing we see, and this has always happened, is smart people like yourselves getting into a business and having a specific need to use the data for some specific purpose, and not having a budget from the business to go and buy a product off the shelf for it. So they go and build a little thing themselves, whether it's Excel and macros or VBA or Microsoft Access or something. And what we end up with is all these little one-off applications spread around a business that do just a little part of the puzzle. And they're not integrated to the broader reporting systems. When that person moves on, that software is left behind and people don't know how to maintain it or extend it. And we end up with, again, with a dependency on key individuals to keep systems working. There's a mineral sands miner in Western Australia where each site has almost exactly the same functionality being performed, but in a different piece of custom software that different people wrote on each site. And now they're trying to bring that up to an enterprise reporting layer, and they've got a different hook into every single site because the systems are different at every site. And worse than that, the data being reported is shaped slightly differently because it means something slightly different to each site in terms of what availability means and how it's defined and so on. So that's what we're trying to avoid. When we look at a whole of enterprise, what we want is consistency, standards, automation, and not a reliance on key individuals to keep the whole thing hanging together. And those one-off applications, I'm not pointing the finger at individuals. They're trying to do the best they can to solve problems for the business that they're in, and that's great. But it does come down to a bit of rationalization over time to say, okay, this is getting out of control. Let's consolidate and put something a bit more solid in place to solve this. So when we look at a mining operation, what we've got on the left-hand side of our screen is the operation side of things. The dark blue boxes is the mining, the processing, the logistics and shipping, all the things we do to achieve the mining operations. On the far right-hand side, we've got the business outcomes. What we're trying to return is earnings, profitability, return on capital, return on investment type things. In the middle are all the things that influence it. So we've got things that we can't control. The sale price on the market, we can't control that. The sales orders in the ERP system from the sales and logistics teams, we can't control that. What we can control is the production, asset performance, inventory management, feed blends, grade controls, things like that. So what we try to do in the area that I work is influence all of these areas so that the business gets an outcome on the right. So what we'll do today is there's a whole bunch of areas we could look at, from downtime and asset utilization to conditional-based monitoring and maintenance. But what we're going to focus on today is a bit of the inventory management side of things. The platform we're looking at can do a hell of a lot more than what we're talking about today, but we'll just focus in on this section for today to deal with the time constraints. So our goal with inventory is to understand what material is available at different points in the value chain and what grade it is, and what that's going to do with our process and planning side of things. So to do that, as I said, we've got different levels of maturity in our customer base. We've got some parts of the operation, like the drill and blast up in Queens that I mentioned, where they're recording data on paper. So it's a fairly immature digitization side of things, paper-based recording. Most companies still have Excel somewhere in the reporting value chain. So again, that's fairly low level of maturity from a digitization perspective, because spreadsheets, while they're nice and easy to use and they're flexible, they make it hard to integrate with and do reporting across multiple spreadsheets and year-on-year type spreadsheet things across multiple files and so on. So when we try to get up to this value chain optimization at the top right here, where we're automating train loadout operations and grade blending at the shipyard and things like that, we can't do that if we've got all that data mastered down in spreadsheets. What we need is digital technologies in the middle here, which have the master data for our stockpiles and our grades and our laboratory results and all that sort of thing brought together. So this maturity curve is what we talk about, a journey that a lot of mining operations go on, where they need to move further up this curve if they're going to get to automation and optimization of the value chain and a digital type world. So what is our goal? Our goal, if we can see the screen, is to have a single pane of glass across the whole value chain. So we'll dive into this in a second, but essentially we've got our mining operations on the left, drill and blast, and excavators and haul fleets bring material up through a processing plant to product stockyards and out to train loadouts and ship loadouts. And we've got a system which can hook onto all those many systems that sit under the hood and bring that data together into a context. Now, as I started this presentation by saying there's some unique challenges in doing this in mining that are quite different from manufacturing. In manufacturing, you've got real-time data, small networks, standalone machines, bottling machines, molding machines. The data's fairly clean and it's fairly sanitized already at the control system layer. In mining, we've got fleet management systems recording haul fleet movements from a block in the pit through to a ROM stockpile. That data is not clean. That data can be recorded incorrectly. The GPS readings might be correct and it recorded the wrong source block. We're continually changing that data at the source, and any system like this that's hooking onto it and bringing that data up for an holistic view needs to deal with data changing at the source. I try to describe this to manufacturing people and it blows their minds a little bit that all the things we measure in mining in terms of weights and flow rates and grades is a lie. It's a close approximation of reality, but it's not accurate. Every weightometer is plus or minus 0.5% or 1%. Weigh bridges are plus or minus 2%. Railway bridges are plus or minus 5%. The data we get is a close approximation of reality, but it's not correct. And what that does is it lends itself to bias, so that what we're putting onto a stockpile and what we deplete from the stockpile are different measurements, and you'll get bias where the stockpile continues to grow in size over time because the instrumentation can't tell us exactly what's being moved around. So that's what I call dirty data. We've got data in mining which is always dirty and it's continually being refined and cleaned, and we need to have systems in place that can take that refined data and recognize data changing at the source and allow you to put corrections over the top of a source of truth, so and reconcile data across the month and things like that, so that we get sanitized data being fed up to our reporting systems. So that's the challenge in mining. The second challenge is that these different systems we're hooking onto provide data in a different time context. So in a process plant where you've got a control system and weightometer signals, you've got nice real-time data on your SCADA system on the screen for the operators. That goes into data collectors for an historian. They might buffer the data. If there's a network outage, you might get an hour's worth of data buffered there. And when the network comes good, it gets flushed through to a historian in a big block. So the data arriving in the historian might be a couple of minutes late. It might be an hour late. It might be a week late if the network's out for a whole week for a remote source. If that historian has remote data collectors for your bore fields operations versus your process plant, the bore fields might be offline for a week, but the process plant's online. So you get different tags coming into the historian that are a different time context. We get non-chronological data. We will get laboratory information systems where there's samples that are coming through fairly close to real time. They're a couple of hours after the fact, and other samples that take a week to analyze and get reanalyzed and come through with an old timestamp, but non-chronological in terms of the data flow. So this is the dirty data. We've got data with different time contexts, buffering and latency of data, corrected data at the source. And what we need to provide an holistic view of the operation is something that can spin all that around and deal with the nature of that data and bring it together in a decent context. So the challenge is that the people who are making decisions for the mining business, the logistics teams that are planning ship loadouts, train loadouts, what they're doing over here is they're responsible for the supply chain. They're responsible for fulfilling orders with appropriate grades in spec, and they're doing it with inaccurate data, which usually arrives late. There's an iron miner out west that I worked with that said that they sample the material as it goes onto the train. The train takes about 8 hours to get to port. They don't know what the grade is on that train until it's almost at port. And if it's out of spec, it can cost them $1 million if it's too far out of spec. The guys who are managing those trains and the loadouts and the port operations are doing it with data which is quite late arriving, and usually when material's already been outloaded from the site. So that's the challenge. What can we do to make data more readily available and more useful to the business decision makers? So this is a view of the Rockwell Operations Management Suite. So we're going to use this as an example of software that solves some of these problems. what we've got in this diagram is the various systems which sit outside the scope of this software that we need to hook onto. So we've got fleet management systems, which might be your haul fleet, your excavators, drill rigs quite often appear in your fleet management system. So all that mobile type equipment down at the mine. And sometimes that's also included in your production side where you're hauling from your concentrator to your rail siding or something. So the fleet management systems that tell us where material is being moved from and to. We've got laboratory information systems that tell us what the grade is at different points in the value chain. Enterprise systems with the production goals, the targets, the geological data, which tells us what the grades in the pit are, what the block model is, the core samples from the mine, things like that. And in the middle here, we've got our grey box. So this grey box is what we call the platform around this suite of software. And what that platform is designed to do is allow you to hook into all these different systems. So there's 150 odd different connectors in the platform that hook onto many different vendors and types of applications and allow us to bring that data into this view. So it's just getting the data. It's not doing anything with the time context, it's just making the data available. The thing that takes care of all those context things are these apps in the middle. So this platform can be applied to manufacturing, it can be applied to mining. These apps in the middle here have been specifically built for mining to deal with these types of data challenges that I'm talking about. So when the inventory management app takes fleet management data and says a haul truck moved material from this block up to the ROM stockpile, it knows how to correlate that to the block model, to the geological data with the core grades, and bring a blended calculation through of the tonnage weighted grade of material that's coming into that stockpile. If that LIMS data comes in 4 hours after the material movements occurred, it'll put that together in the right time context once the data becomes available. So these modules that we're going to talk about and demonstrate today have been designed to handle some of that dirtiness of data that happens. Down the bottom here, we've got our process facility. So this is our fixed plants typically with a process historian, APC, MPC type advanced controls, condition monitoring, all of our high density, high frequency data that comes from fixed plant operations. So again, we've got second or sub-second type data coming through here and much slower data coming through from these types of systems over here. So we've got different time contexts being mashed up together by these apps. So across those apps, I'll just give you a quick summary of some of the typical things that get done by these apps in mining. Downtime accounting is typically the first type of application that gets deployed in mining. The asset infrastructure in mining is very expensive. What companies want to do is make sure they're getting assets available and utilized. So downtime accounting tends to be the first point of call for MES types of applications in mining. Following on from that, production reporting, understanding what's been produced, the grade that's produced, what's been consumed, things like that. Followed by inventory management, so stock balances, grades on stockpiles, feed blend operations, things like that. And then down to metal accounting and so on. So there tends to be a typical maturity curve again with the deployment of different applications in mining. Today we're going to focus on this inventory management side of things. So if we take a typical mine site, we've got a mine over here where we've got drill and blast operations, excavators, haul fleets bringing material across to a fixed plant. In here we're crushing, grinding, flotation cells, gravity circuits and so on to separate materials. It might be physical separation or chemical separation depending on the type of mineral we're dealing with. That comes out to product stockpiles. And on here we've got stockpiles in the iron industry here that are 3/4 of a mile long with long stacker reclaimers. So segmenting that up and understanding the grades of different parts of the stockpile is part of what we'll talk about today. So this is a typical process flow. And what we need to be able to do, if I jump to one of my diagrams, which is not as pretty, is through this value chain, we need to be able to pick up data from the geological system, drill and blast, and things like the core grades and the drill grades coming from here, the haul fleet that says where material came from in terms of each block through to stockpiles. We've got a customer up in the Northern Territory which has 42 ROM stockpiles. These are finger stockpiles based against a cliff. So the material that they dump on the tail end of it is the first material that gets pulled off. So that's what we call a last in, first out material model for that stockpile. So keeping track of the material sources coming onto these stockpiles and which source feeds the crusher allows us to identify what sort of blend we're putting through our fixed plant. So this sort of data can be quite broad ranging. 42 stockpiles is the most I've dealt with a customer in ROM stockpile management. But it sounds like it's a lot of work to go and model that. But essentially at that site, what we're doing is hooking onto that fleet system, and we've got one data capture rule that picks up the source from the fleet system and dynamically assigns a ROM stockpile source to all the movements coming to the crusher. So it's a fairly simple configuration in a platform that supports this type of thing to be able to hook onto all of this broad, large scope data and model it nicely. So once we get into the fixed plant, we're dealing with that different type of data. We've got sampling going on at different points, typically composite samples across a time range. So on a feed conveyor belt like this coming into drum scrubbers, you'll have a cross-cut sampler. Cross-cut sampling takes a little slice of material every few minutes, puts it in a bucket on a carousel. Someone will walk out after 4 hours or 12 hours and pick up a bucket from the carousel. The timestamp of that sample is when they pick the bucket out of the carousel. It's at the end of the sampling period. So when the system goes and joins a weightometer set of values here to say how much material came through here with the grade, it needs to take that timestamp from the sample and correlate it to all the movements prior to that timestamp back to the previous sample, because those are all the movements that got collected in that bucket. So that's what we call a retroactive sampling model. So in this software that we're talking about today, using to demonstrate this, there's a tick box that says, for this lab data, when I'm correlating it to movements, is it retroactive model or is it a proactive model? So that sort of cross-cut sampling is retroactive. If you've got an online analyzer on your train loadout system, that would be the opposite. The sample that's taken there applies to the movement timestamps after that point in time. Your core grades and drill grades apply to movements after that point in time because you drill, blast and sample at the beginning of the shift and then excavate for the rest of the shift. So having software that can spin that data around based on the different sampling methodologies, software that understands that our ROM stockpiles are dumped on the tail end of that ROM finger and pulled from the tail end. So it's a last in, first out sort of model when we're tracking material through here versus a crushed ore stockpile which is fed from the top and extracted at the bottom. So it's a first in, first out sort of model. Being able to have software that you fairly simply just set up the different models and it deals with all the complexity of data, the latency of data, late bound arriving data, buffered data being flooded through later on. Letting the platform deal with the mess and putting a model in place that allows us to profile our flow is what gives us value here. So in this value chain, what we really want to do when we're loading out to trains and we're trying to fulfill targets for logistics is understand what the grade is on these stockpiles. So as I said, some of these stockpiles can be 3/4 of a mile long. You've got a stacker that's got a different stacking operation depending on your stockpile modeling strategy, and being able to profile that across that 3/4 of a mile so that when the reclaimer comes through and starts excavating from this area of stockpile, we know what grade we're pulling off. That's our challenge. How do we do that without writing crazy pieces of macros and code and things like that to model this? There's an iron ore customer that I worked with out west where they don't do any sampling through the process plant. They've got their core grades from the block model up here, and there's a metallurgist, senior metallurgist, very expensive resource, who spends his entire day, full-time job in a spreadsheet, trying to model fleet movements up to the ROM stockpiles, into the crusher, through the plant and onto these stockpiles so that he can try and predict the grade up here. It's a crazy amount of work. It's all manual. He's massaging the data himself, so there's no transparency as to where the data came from. And he's doing his very best, but it's a crazy sort of operation this day and age to be doing all of that with a senior metallurgist just to profile these stockpiles when we could model it with software. Now there's challenges with modeling it in software. You've got gaps in the data. Typically in mining, we measure some of the key feed points, but we don't measure the water addition into the flotation. So we don't measure reagents and fluxes. There's a whole set of things we don't measure. So we need to make assumptions and put appropriate models around those. But if we've got the right instrumentation in the right places and we've got enough information, we can deal with it. And sometimes when we get to things like this coarse circuit and fine circuit through here, we need to treat that whole circuit as a black box where we know what's coming into it, we know what's coming out of it, but we don't necessarily have to model every little detail that's inside of it. If that's a fairly straightforward process flow, like a spiral circuit in iron, that's okay. If we're in copper or gold where there's regrinds and secondary flotation or circulating flows, we might want to put a bit more detail into the model in those circuits. So how does software help us do that? I'm going to make this a little bit technical. I'm going to dive into a model here which talks about a LiFO, last in first out storage model. This is a diagram that software developers use to describe what the software is doing behind the hood. But essentially over time, we've got material being added into different storage nodes here, which are stockpiles or shipping containers or whatever it is that holds material. And as material comes in here and gets added over time, the first material that gets depleted off here comes from the top of the stack. So the challenge with that is if we put some material on and deplete some of that parcel, but not all of it, and more material comes on, the next piece that gets extracted is from that new material, not the remainder of the partial stack that we've already partially depleted. So we end up with a lot of data fragmentation, and if we need a fairly intelligent rule set that sits behind this that knows how to put all that data together across the different fragmentations and time periods. We don't have nice regular time periods in mining. A train can arrive at any time, it can leave at any time, bypass gates can flip at any time. We don't have nice regular 1 hour intervals that we can slice data up into. The system has to deal with all these fragments of time and fragments of balances as it puts this data together. So this is a diagram describing what a LiFO model is. There's another diagram for FIFO, which is the first material that comes on here is the first material depleted. And again, we get that problem with fragmented data where we put 1,000 tons on here, we deplete 250 tons and then put another 1,000 tons on. When we deplete the next 250, it's still coming from the bottom of the stack. So this model is not too bad. When we get to homogeneous, this is the nasty one. When we put material on here and deplete a part of it, and then put more material on, the next depletion is a ratio of all the residual material parcels that are on the stockpile at that time. So we end up with things like the crushed ore stockpile that's feeding a coal prep plant is notorious for having a bulldozer on it that's pushing material around to manage the stockpile, push material off to the side for a while because they've got a flood of material, and then push it back into towards the underground feeder. So as soon as you've got a bulldozer on a stockpile, all your software models go out the door. You can't do a pure LiFO or FIFO model for something where there's a bulldozer pushing stuff around. So those types of stockpiles we typically treat as homogeneous. And you need fairly sophisticated models sitting behind all that data to be able to deal with the fragmentation and cleanup of data as parcels head towards a fractional component as the ratio of depletions occurs over time. So you can see here it gets a bit messy over here. So this is a diagram describing what the back-end engine behind the software is doing when we've got an homogeneous stockpile model going on. So if we go back to that long travel stockpile that we're talking about, this is our 3/4 mile long bed. We've got stackers going along here that might be doing cone stacking or chevron stacking where it does a long travel pass and so on. This is an example of using those sorts of models to build up what we call virtual stockpiles at different partitions along the bed and allow us to segment material parcels on here over time. So if we're doing a chevron stack, we're doing a long pass and then a long pass, we might end up with small amounts of material here from the first pass and a bit more from the next pass and a bit more from the next pass. When the reclaimer comes along, we want to know what the composite grade is that's been put into this pile for when we pull it out. So we could treat that whole section of the bed as homogeneous. We could do something a bit more intelligent. It's what we call homogeneous block LiFO, where if this is capable, this bed partition is capable of holding 10,000 tons, we might say model this as 1,000 ton blocks, where the first 250 tons from the first pass and the next pass and the next pass all add up to 1,000 ton block, and then the next block and then the next block is virtual blocks within this partition. What that allows us to do is, if it takes an hour for this stacker to go past and come back, we've got a bit of material at the bottom of this stockpile which came from one pass and one lab result, and another parcel from another lab result, and so on. So each of those virtual blocks that sits in here gets treated as homogeneous for a quality grade, but each block is treated as LiFO for the purposes of reclaiming. And that then gives us a better approximation of reality when the reclaimer comes through to say, the grade we're getting out of this partition at this time is a blend of these different passes of stacking operations. Because when we put stacked material on top of here, it doesn't just sit on the top, it dribbles down the side, it slumps, it flows, it does weird stuff like that. So that sort of homogeneous block LiFO, homogeneous block FIFO, additional layer of modeling above the standard models is what allows us to more closely approximate reality when we start saying what's coming off this blend. So that's kind of the technical side of things. I was told to make this session a bit technical for the audience because you guys are apparently got quite a few grads and postgrads in here. So that gives you a bit of an idea of the complexity of software sitting behind the model that allows us to do this. If we jump over and start looking at how we use that data, what I've got here is a demonstration system. This is based on real world data. We've got data that customers provide us for fleet management systems, and we've obviously changed the data to protect the customer, but we've got real world data sitting behind this demonstration system that we're going to go through. So what we're looking at here is a dashboard, which is what we call a single pane of glass from the drill and blast operations through the fleet system up to the ROM stockpiles, through the process plant where we've got historian and LIMS type data, rail loadout and logistics through to port. And we've got a system that hooks onto all the different underlying sources of data, from laboratory systems to geological systems to fleet systems to historians, and pulls all that data together into a single view of the world. And we can then run KPIs over that and algorithms to profile data and give us summary information. If we dive into one of these particular operations, we can build our own mashups in here. It's all web-based content to create views of information which are relevant to our particular value chain versus a different mine site. So drill and blast data, shovel and load, and so on. What I'm going to do is dive across to the stockpile modeling side of it. So what we've got here is a plant model down the left where we've got our haul fleet pulling material up from our mine blocks coming into ROM stockpiles. We've got different views of data here for the grades, the balances of the stockpiles. We're then going through a primary crusher and into a fixed plant process where we've got drum scrubbing, secondary crushing, fine circuits and so on, thickeners and so on, and then out to product stockpiles and a train loadout operation. So we've got a whole value chain built into this demo. What I'm starting with here is at the ROM stockpiles. And what we've got here is data that's coming from the mine through the haul fleet and up. So the data here is coming from a Wenco system that was provided to us. We've changed the data to protect the customer, but it's real world fleet system. And if I go and look at the haul truck timeline, this is the Wenco data that's been transformed into a swim lane for each truck. So these are all the trucks in the haul fleet. And these are all the operations that occurred to each truck over this course of time. So we've got operating standby events. We've got unplanned mobile downtime where it's off route and being rerouted to a different mine area. We've got haulage operations going on. We've got fog events. We've got all these different events that happen to the trucks. So this is kind of a downtime view of those trucks. What we're really interested in is the truck load. So if I go and look at the loads of these trucks over time, I'm looking at a week's worth of data up here, and I'm grouping the data by shift, and I'm showing the data by individual truck. So down here, I've got truck number 23 across this shift between 6 and 6. It pulled from a strip and block in the mine for a total of 453.25 tonnes. It also pulled from another strip and block, B13, for another set of tonnes. So this truck got routed to 5 different sources over the course of this shift and pulled a total of 1,800 tonnes for the shift up to the ROM stockpiles. And you can see here it's tracking whether it went to stockpile 1 or 2. So this is taking that fleet data and transforming it into what we call material tracking movements that say where did it come from and where did it go to. The source is important because these sources have geological data associated with it that tell us what the core grade is. So based on these tonnages, we can say if the grade of this block is 43% and the grade of this block is 46%, tonnage weight the grade so that when I go and look at the grades coming into these stockpiles over the course of this shift, we can marry up those grades and tons and get a tonnage weighted profile. So we can see up here that I've got this split up by fairly granular time intervals, 45-minute time intervals. All those truck movements are being split up to say the tonnage weighted grade of iron coming into this stockpile across this shift is 47%, 46%, 43%, based on all those different sources in the mine across time. Similar with moisture. So when we look at data like this, we've got gross weights, which are wet weights in the trucks or wet weights on a weightometer. And when that parcel material gets taken from a crosscut sample to the lab, or the core grades get sampled, they take the wet weight, measure that, dry it out, take the dry weight, and then the iron grade or the metal grade is associated with the dry mass. So it's a percentage of dry mass. So what we need to do when we calculate things like the iron grade here is take the wet mass times 1 minus moisture times the iron to get that dry grade that's going on here. So there's a fair bit of math going on behind the scenes. We can define those algorithms to suit different types of sampling methodologies, different types of data. But the engine itself is taking care of the time correlation of the whole load occurred at 10 o'clock and the lab data came in 5 hours later, but back timestamp to 10 o'clock and correlating those up and putting them together. So that's an example of geological data and fleet data being put together. Similarly, if we go to our primary crusher where we've got different sources but the same type of data profile, on here we've got historian data for a weightometer depleting from the or processing material through the crusher and putting it onto a crushed ore stockpile. And we've got lab data coming from a LIM system instead of a geological system that we need to correlate with this. So similar sort of thing, we've got material coming into the crusher and out of the crusher. We've got a running balance over time of our crushed ore stockpile, and we can put that data together to say what the grades are of material going through that crusher and going onto the crushed ore stockpile by correlating LIMS data with this. Now, if that LIMS data doesn't come through for 12 hours, the system will calculate the grade on the most available data it has, which was the most recent lab data. Once that new sample comes through, backdated to when the sample was taken in the field, we refresh the dashboard and it mashes it up. So we don't need to wait for the system to go and recalculate things. These calculations are being done on the fly so that it's always using the most recent data when it's making calculations about these different grades. We're running out of time to go through everything that I wanted to, but I think you're getting a good idea of a platform that hooks onto different sources and mashes data together in a time context. If data is delayed due to network outages, it'll process it once it comes through and then fit it into the model and calculate things on the fly with the most recent data once it's available. I'm just going to talk about loadouts for a second, because at the loadout operation, we've got a slightly different type of data. In our fixed plant, in our mining operations, most of the reporting is done by shift or hourly intervals, nice regular time intervals that we're splitting and dicing time up to. At the loadout operation, we've got irregular time periods. A train turns up at 7:15 in the morning and leaves at 10:35. So we need to go and pivot all our data around a time context based on the train arrival times. We can see there's then a gap through to 10:45 for the next train, and then a gap from 1:30 to 4:30 for the next train. So what this system is doing is looking at, instead of looking at nice regular patterns like shifts or production days or production weeks, or periodic intervals such as hourly, 2-hourly, 4-hourly type intervals, we've told it to go and look at the train ID, dynamically determine the times of train presence on the site, and pivot the data automatically around those times. So for this train here, we pulled from product stockpile number 2. The total mass that was depleted was 5,200 tonnes. I'll just drill into this a bit for you. And in that 5,200 tonnes, we had a bit of iron, a bit of moisture, a bit of alumina, a bit of silica based on those lab results. So the system is dynamically calculating the constituent material mass of iron within this wet mass that went on the train. We keep the constituent masses separate from our gross masses so that we don't accidentally double count material. The reason this number is higher is because we've got dry mass here as a constituent material, and iron is included in both the dry mass and the wet mass. So if I just jump in here and put a filter on this, so it does not contain dry mass, we get a better idea of the materials we can account for within this overall mass on the train. So typically when that train goes out, we've measured this based on a weightometer set of signals. Quite often when the train arrives at port, you'll get a customer weight that they record down there that's quite often more accurate than what we've outloaded up here. So we need to be able to come in here and correct this data. So in this example, we've got 5,200 tonnes that we recorded. The customer comes back and says, actually, it was 4,900 tonnes that we recorded coming into the site. We can put reasons against these and record why we're doing changes to data and put notes against it for auditing purposes. But essentially all those weighterometer movements that occurred across that 4 hours of loadout, fairly granular data. This change that I'm doing will go and pro-rata that change across all of those underlying movements and we'll adjust it. And you can see here our iron mass has been recalculated on the fly as soon as we made that change and reconciled that value. For transparency, if I go and show a bit more data, we've got columns here which show us what the original quantity was and the override quantity, and there's a whole audit trail behind it, so that we've now got accountability for data integrity. We can see when data was changed, who changed it, why they changed it. If I go to the audit notes, I'll see who actually made that change, and we've got flags here to say this data has been edited. So instead of spreadsheets where people are manually updating data and feeding it through, we've now got a system where all of that audit trail, the transparency and integrity of data is visible to everybody. So that's all built into the platform that we're looking at. And all these calculations you can see updating on the fly as we need them to. So what's our end goal? Our end goal out of this facility is to recover as much iron as we can. So I'm jumping to a screen here, which is taking the metal tons fed into the crusher based on the cross-cut sampling and material coming into the crusher, the loadout sampling and the loadout tons going out. And this is, pardon me, dynamically calculating the recovery and yield across the last 3 days, broken up into time intervals from all that data. So this is kind of a layer on top of your metal calculations, where we calculate the metal tons fed in, the metal tons fed out. And if we divide metal tons out by metal tons in, that gives us our recovery. So recovery here is varying over time, and our yield is the metal tons out divided by the gross tons in this case. You can change these calculations. These are all definable. Some people define yield as the gross tons out divided by gross tons in instead of metal tons out by gross tons in. All of that's under your control. So this is the system taking all of the constituent material calculations and then putting another layer of algorithms over that to get KPIs like recovery and yield out of the system. So that's kind of the nuts and bolts of a system that hooks onto all our different sources of truth, deals with the dirty data, allows us to correct data if we need to. If your data is coming from an historian, typically you don't want to override the data in the historian when you correct it. You want that source of truth to say exactly what the instrument measured. So these corrections that we're doing here are a layer above that, which is allows us to correct it, pro-rata it across the interval and all the granular timestamps, but come back with the right results. So what we might do is maybe open the forum up for some questions. If you want to put questions in the chat window, we should be able to answer them from there. Might be better than audio. Fatih, did you want to moderate the Q&A session?
Yeah, thank you very much for the amazing platform and presentation. So, like we have something like 8 minutes for questions. So if anyone has any question, please. I had a question. Can you hear me all right?
Yes, I can.
At the very beginning, you mentioned that there's a lot of data that you need that's not captured and captured but not needed at a mine site. Does this inform that kind of conundrum as far as you start using this software? Does it answer that question and like add clarity?
Yeah, so it becomes pretty apparent when you start building out your model. So we did a recent job for a customer in Western Australia, and it's a greenfield site, and they'd put instrumentation in for all the places they needed it for control purposes. And when we went through and sketched out the model of how we were going to model this type of thing and split out material flows between different sub-circuits, it became apparent that there's quite a few sections of plant which are gravity fed and they didn't have flow meters. And as a result, we couldn't actually tell them how much material was going into their flotation circuit, as an example. Because we couldn't do that, we couldn't tell them what the yield was in their attritioning circuit. So when you start defining a model before you build your software model, typically we start as an engineering process with Visio sketches of the different circuits and the flows and where the instrumentation is, and we identify fairly early on where the gaps are. The platform has the ability to put virtual sensors in. So if there's enough instrumentation in other places, you can create a virtual sensor that derives the flow at different points. For that particular customer, there wasn't. There were too many recirculating flows that were also unmetered to be able to do a virtual sensor that told us what that flow was. But in a lot of cases, you can do something simple like a tank has a flow meter coming in, but nothing coming out. And you've got the level in the tank. So you can infer the output flow from the change in level in the flow in and putting an algorithm around it and create a virtual sensor for the output. The risk with doing that is you make assumptions when you do that. If there's a leak in the tank, you won't be able to detect it, for example. If there's bias in your instrument, you won't be able to detect it. So there's two key things that I tend to focus on with customers is where are the critical points of egress and inflow and outflow of the different circuits, and are they metered? And are there things coming in which we can't account for? Do we need additional instrumentation, or can we infer it? Can we isolate it from the algorithm so that we exclude the water completely from the material model, for example, and just deal with the metal tons in different places and do all that tracking through metal tons? So depending on the facility. The other thing I should mention is there's some pretty advanced instrumentation out there these days. So in gold, if you're looking at a carbon in leach circuit, typically what they'll do is take samples across the shift and have a composite sample at the end of shift. So 12 hours of sampling, send that off to the lab, and another 4 or 6 hours later, they get a result back. And they then make changes to their carbon impregnation set points and stuff based on information that's now 12 to 16 hours old. So it's a very slow sort of response. And if you've got a change in feedstock that influences the dynamics of that circuit, you're making very late changes to it. There's a company called Gecko Systems that has an online gold analyzer, which it's fairly recent innovation, but it's like an example of a modern instrument that can plug into that circuit and give you near real time, like 15-minute intervals of feedback as to what your gold is, or Carbon Scout is another product they have that does the carbon circuits. If you've got advanced instrumentation like that, you can do something even more intelligent where you take that and stream it into the platform. This platform is an IoT platform, so you can stream it into there, feed it up to machine learning algorithms, make decision response decisions up there and feed it back to the operators as recommended set point changes and things like that. If you put enough confidence into that and rules around it, you could write directly to the set points in the control system, do closed loop control. That sort of thing scares people. They like operators to be in control of that stuff. But conceptually, it's no different from your APC algorithms down at your control layer that are doing high-speed response type control. This is just designed for much slower response and machine learning type intelligence instead of that PID type intelligence. So there's a lot of stuff you can do these days with those advanced instruments. If you end up in those sorts of circuits, it's worthwhile having a look around at some of that innovative instrumentation that's out there and what's available.
Thank you. Yeah. Well, we have a question in the chat from Jeff. It says, how difficult is it and how long it takes to go from manual data input to automation? What are the change management challenges when doing so?
Sure. So I think the fastest project we've ever done is 5 weeks. That was a small gold facility, a fairly simple circuit, crusher, sag mill, ball mill, grind type stuff. Large scale projects can be around 6 months for a full blown downtime inventory accounting, the whole kit and caboodle. So that's the sort of time frame. But in a lot of cases, what we find is most of the data we need is already in place. We've got historians and lab systems already in place. They're just not being integrated in a useful way, or they're being done manually in spreadsheets. So in a lot of cases, the core data we need is there. You do end up rocking up to sites where they've got a fleet system, but it doesn't tell you the source destination. It just tells you the truck ID and the time it went and the activities associated with it. So there can be gaps at times, but most mine sites are measuring things fairly well, and they mostly have their lab systems in place. Whether it's labware or CHD or whatever it is, doesn't really matter, as long as they've got some data there. The platform itself makes it easy to integrate to those and hook onto them. All the hooks are there to hook onto those different types of systems. So it's really about getting the model right, understanding the dynamics of the physical process, and being able to build that into the model. So I've been looking at the summary dashboards over here. Sitting behind this is our plant model that's got all of our granular detailed sort of process plant for drum scrubbing, secondary crushing, downtime events, material movements, and all that sort of granular stuff. So building out the model, designing that is where some of the skills come in to get that right.
Well, thank you very much. Does anyone? Okay, we already like at the end of our time, so I would like to thank you all, and thank you, Richard, for your presentation. And just a reminder, we have our seminar every Wednesday at 4 p.m. We also upload the recording on our channel so that you can watch the seminar. And thank you again, Richard. See you next week.
Okay. Thank you very much, everyone.
Thank you.